Hello, my name is Jeff Cox. I am the engineering director in charge of the Build, Test, Deploy group at Google, which includes the Bazel project. I'm here to introduce our keynote speaker for today, Melody Meckfessel, who is our Vice President of Engineering. I've had the luxury of working with Melody now for, I think, 7 years. Enjoyed every minute of it. And she is here to talk to us about testing, how testing yields velocity. And I will have the important job of running the clicker.
Thanks, Jeff. Can you hear me? Okay, good. I can't see you, unfortunately, but excellent. Thanks so much, Jeff. It's really an honor to be here today, to work with Jeff and to work with the team and to be part of what is a growing community around Bazel. I lead the DevOps team at Google, and really what that includes is source control management, build, test, deployment, operations for services running in production for almost all Google developers. And that includes Chrome and Android and teams doing open source development like TensorFlow. But today I wanted to focus on testing, near and dear to my heart, and talk a little bit about the benefits of Bazel. So if you could go to the next slide. And then can you put the slides back on the projector? There you go. Thank you. So we know, as engineers, the benefits of testing, pretty well known, makes our code better, which in the end makes our users happier. And I'm not going to be able to see the hands raised, but how many people in the crowd, in the audience, have carried a pager? Jeff, what's the approximate percentage?
Some, maybe not enough.
Okay, so I just want to point out the uptime, right? The quality of the code that we write, we wanted to make it out to our end users, and when I'm going to hit on this point a couple of times in this talk, but when we compromise and we implement workarounds, we're impacting the quality of what we're delivering to our end users. And if we don't carry the pager, we're probably impacting, the humans that are keeping the service up and running. So I think those are important motivators to remember that this has an impact on multiple people, our colleagues, our users. And the surest way to make, I think, any developer angry is to slow them down. And so, I think that's where automation comes into play. We can get the quality that we need to at scale and have this sustainable growth where we keep making our code better, we keep growing our application, and we keep the sustainability around how to have that growth in a rational way. So, there's no pros and cons on here. It's all good. It's all green. Why we should test. So next slide. So great. We're writing tests. We're testing all things. But next slide. It's not quite the full story. So, Google has done some studies, and there's many that are published out there across hundreds of organizations, and we've found that through that research that the testing practices are really falling short of what the ambitions or the targets are for teams. So very few teams are running tests at every code change, and even fewer have instrumented their entire code base to be able to exercise every code path. So it's very, while it's very common for most teams to run kind of like a full test suite once a day or maybe less than that, it's that the completeness of that test suite is usually not sufficient. So even if we know it's good, we're not doing it enough, and it is impacting quality. So let's do some root cause analysis. So why aren't we testing? If we know as engineers that it helps us find defects before making it out to our end users, we know it helps our velocity. Why aren't we doing it? We have very good intentions as engineers to test. So next slide. What we found, keep going, is that we sort of hit this reality, which is a set of trade-offs that we have to make. So we add tests, we increased our test coverage, but then testing takes more time and resources. So it starts to become a drag on our productivity and our velocity to get features out the door. And so, probably most of us in the audience have kicked a build off and gone and done something, had lunch, had a coffee, talked to a friend, went for a walk, and come back and it's potentially still running. And so we start to make these decisions. Well, maybe we shouldn't test everything. Maybe we should just test some things. And that gets us into a trade-off situation. So next slide. So we find ourselves in this conundrum where more testing leads to higher overhead. It leads to less defects, which is what we want. But as you increase your test practices, your code gets better and better, right? But your build and test may take longer and longer. And that means you need more and more hardware. You need more and more resources to be able to execute those tests. So this puts you as a developer, you as a development team, you as an engineering company in a really tough kind of situation where should you take the extra time to run a bunch of tests that may not reveal any problems, right? Or should you, get that application out to your users as quickly as you can and risk shipping a defect? And so, for the human that's carrying the pager on your team that's going to have to deal with the defect, or for the impact to the user communities of that defect, it's a tough choice. It's a tough choice to make. And so I think what a lot of us are trying to figure out is what is the sweet spot when you have to make this decision around these trade-offs. You can ship it right now, or you can wait and ship it correctly. And so, going back to some of the research that we've done, even teams with, elite DevOps teams that have the most sophisticated testing practices, their number one challenge that's stated is balancing test frequency from resources, right? Because it's cost and time. And so we're trying to figure out what is the right balance there. So next slide. So if we take a step back and talk about why we test, I think this is pretty clear. Like, we want to create a great user experience for the code that we're writing, for the application that our users are using, and we want to avoid the operational issues, right? Because users expect high uptimes. Just think of the apps that you yourself use. So we're really trying to get rid of the errors in our own code, but we're also struggling with what our dependencies are. So, these days, very few projects, if you go to the next build, Jeff, very few projects own the code all the way down to the hardware, right? We are, as developers, depending more and more on libraries, on services that are not developed by us, that are open source. And that's great, right? Because we get to reuse code and we get to focus on the thing that, that we're good at, that we want to build. But even really small systems have a ton of dependencies now. And that, depending on something you don't own, can be really challenging because we're all having to handle kind of this very rapid state of change on things that we just don't control. Next slide. So what's our ideal? Where our ideal really is that we're integrating those dependencies, right? We are integration often and everywhere, right? So we're trying to make sure that we don't have to do a ton of pre-release testing. We're just making sure that we're testing the dependencies that we have, and we're doing that everywhere. And this is really what underlies the whole practice around continuous integration, which is really to increase our velocity. And there's an interesting part here around security, right? So if we're trying to protect ourselves, that integration of dependencies is going to require testing. And if we're doing it frequently, it's going to require even more testing. So you can see how this all, really just builds on itself. Next slide. And when we talk about CI, right, where we're continuous integration all the time, frequently, it can be particularly challenging. So you can see, right, as the size of your code base increases and the frequency of your testing, your integration increases, so does your testing overhead, right? Like, and then that starts to drag on developer productivity. So the thing about dependencies is that in order to really vet those dependencies every time you integrate, you need to make sure that you're testing everything that they depend on. And this just is leading to a lot of testing time in our development process. So next slide. So where do we want to be? How do we find that sweet spot where we're testing the right amount to improve our test hygiene without these negative effects of slowing us down, hurting our productivity, or radically increasing our test infrastructure and the cost associated with that test overhead? So next slide. So I want to tell you a little bit about how we do automated software testing at Google and how Bazel plays a key role in this. So at Google, we've invested a lot in allowing developers to test in a way that helps us move very quickly and hopefully not break things on a really large code base. So automation is at the key of this. We couldn't do it. I think engineers would be incredibly unhappy if we were slowing down their velocity. So we've added automation, and a lot of that ties back to the build system, or Bazel. And we've learned a lot from working within the Google engineering community. And so part of what we're doing is we're starting to take these out into external communities. Bazel is a great example of that. I remember Jeff and I and various members of the team were like, we should really open source this. This is something that everyone could contribute to and make better. And then there are other tools like Cloud Build, Build CI and CD in the cloud that we're making available on GCP in our cloud platform. So I'm going to just talk for a couple more minutes, and then really we want to get into doing demo features. But I just wanted to say the whole reason we're doing this conference, whole reason we open source was so that we could build it together. So I know myself and everyone on the team is really interested in hearing what of these ideas resonate with you. So next slide. So this is, I call this the vanity stat slide. Numbers are interesting. I think there's a couple interesting bits here. But for any one of these, like for the commits, for the builds, for the number of tests, for the code reviews, I don't think we could do any of this without the infrastructure and the automation behind it. So my team has really just put the focus on automation as much as we can automate, as much. We're going to talk in a second about intelligent test execution, making the best use of resources so that engineers can move quickly. And next slide. So, is any of this Google experience relevant to you? I think likely it is. Now, the code size, the scale or the increase of the code base itself may, are different possibly, but the benefit of the test automation, I think, is still there for all of us. It's important for everyone in the community, because if the intent is to get those features out to our users quickly, with the expectations that they have of quality and of uptime and of security, I think that's really a common goal that unites all of us in this space, and Bazel can help with that. So our test, next slide, our test automation is built around some principles, and so I wanted to share a little bit of those principles, and those principles factor into the decisions that we make about how we build the infrastructure. And they really build on each other in terms of how we think about the build system and the role that Bazel plays in it. Next slide. So we're going to start to the left and move our way across. So first, we want to run only those tests needed to validate a change. So why is that important? Next slide. So as you know, in Bazel, we declare these logical groups of sources and tests, and we call them targets. And the idea here is, how do we break down the source into small autonomous units that Bazel can understand, right? That we can process as efficiently as possible. Next slide. So then we take these targets and we determine the units of build and test execution. And each unit of execution, we call that an action, right? So you can see the action that we're going to take. And that has a fully specified list of, inputs and outputs. Next slide. So then those actions get pulled together into a graph. And the output of one action becomes the target or the input to the next one. And we treat, you see in this diagram here, right? We treat test actions just like compile actions. So we're treating them the same way, build and test actions leading to the artifact that we want to create. So next slide. So we really, again, sort of principle, run the tests that matter, make best use of the resources, have the fastest velocity. So let's say that you built and tested your code once, and this is the graph of action. So say you make a change, and if you can just click Jeff, and then you need to figure out what you rebuild and test of these elements, that everything that they depend on. So click again. And then you can see here with the original graph, we don't have to rebuild and test everything, right? We're checking the dependencies and making sure that we're only testing the things that need to be retested. So next slide. So that graph and the composition of that graph is really important because this determines the sort of development time performance that that we're going to execute on. And we're not going to construct the full graphs with the 10 million nodes, but constructing that graph and then being able to understand like the small fraction of the graph that we need to test is really important. At Google, we construct the graph across all dependencies, multiple languages, multiple platforms, and it's not just about the code, it's about the tools as well. So we're really trying to model all of those targets and actions and the dependencies between them so that we are minimizing the number of tests that we need to run. All right, next slide. So the next principle. So we want to separate the well-behaved tests from the not so well-behaved tests. So next slide. So we have two big buckets here to think about: hermetic and deterministic, and non-hermetic and deterministic. So we want to ensure that as many tests are in this HD category as possible. And by separating them out, we can only run them when we need to. Bazel still supports being able to run non-HD tests. But really, if you click the next slide, we really only want to be running those HD tests when dependencies change. So again, really trying to figure out the highest quality tests and that we're running them constantly. Next slide. Okay, reproducibility, super important in terms of controlling the test environment where we're executing the tests. So next slide. So it really is about ensuring that hermetic and deterministic behavior of tests. So we design the runners and the execution environments to support this. Sandboxes, things like emulators for mobile devices, so that things are ready to go and controlled. I know at Google, flaky tests are still an issue. When developers may think that they're hermetic and deterministic, but they're not when you look at the data, when you look at the execution. So we've defined some services that help spot those flaky tests so that we can take action on them. And there are Bazel features that I'm sure we'll talk about today that mitigate that flakiness, doing things like automatic rerunning on failure and being able to flag the flakiness over time. So those are important principles in testing that we've factored into Bazel. Next slide. So we want to distribute test execution, and we want to cache as much as possible. So again, if testing is about quality, right, while maintaining our velocity, we want to make best use of the resources that we have. So next slide. So this is the graph that we just saw a minute ago. And the green nodes are the minimal set that we need to rerun. So if you click again, I think it builds, yeah, these blue. And so you can see here, right, there's no dependencies between them. So we can run them in parallel and speed things up. Next slide. And this was the other graph from a second ago. These actions, right, each one of these actions can either be executed locally on whatever the machine is that you're running Bazel, or remotely in the cloud. So we're trying to design for parallel execution. Next slide. And we compute a signature for each of the action based on the inputs and the functions that it computes. And then the results of these actions, we cache them. So that if the inputs don't change, we don't have to regenerate the output. And these cached actions are shared across users and Bazel instances. So caching is just a critical part of how we've been able to control the test costs within Google. Yeah, there you go. Caching has been a huge win for test execution and just performance and expectations of the users of Bazel. Next slide. All right, there's a couple more slides, and we'll do the demo. So, point I want to make here that I think I already mentioned earlier is that Bazel does interoperate with different execution environments. So you can see here, Mac OS, Windows, browsers, mobile emulators, physical devices. It's important that we support continued evolution of the execution environments, and as they change, that the build system supports them. All right, next slide. So shifting left. So again, if we want to catch things before they make it out to users to have a negative effect on what we're building, we want to shift left. And this idea of shift left is not just for tests either. It's for things like finding security vulnerabilities and doing vulnerability scanning before you push out to prod. So the next slide. So we're really trying to shift as many tests left as possible. So you can see here, matrix, right, of testing. Google's testing infrastructure, we're regularly running thousands of unit tests per change. And that same Bazel infrastructure is being used for all of the hermetic and deterministic tests. So, we can easily move tests between different tiers. This whole principle of catching things before they affect other teams, you can see with pre-submit, right? We're trying to catch things before they're going to break anyone else, which I think is just, it's good engineering, good collaboration. We have a norm for post-submit that we will just automatically roll back and ask questions later. And that's a policy decision, right, that you can make as part of your testing practices. But the goal behind all of these, the implementation of these principles, is to make testing so fast and easy that as developers, we will want to write tests and we won't be put in a position where we're making those difficult trade-offs. So really a lot to think about in terms of the impact that it can have and the cascading effect. So final slide here. We are showing test results in this aggregated dashboard. You can see here, tests are at the top, commits left to right, light squares, tests that weren't affected, really helpful to see. Easy to identify where tests failed, very clear, like indicator here, and flaky tests that are highlighted. Really, I think there's still a lot of work to do to keep up with what's occurring in development, especially as it relates to cloud. I think we're all struggling with dependency analysis and testing as it relates to that, and in this situation where we're looking for help, we're looking for tools and infrastructure to help ourselves have the highest quality code as possible while maintaining the expectations of our user communities. So with that, I think we have the demo next. And I just wanted to say thank you so much to everyone that's coming. I know last year was our first year, and it's great. It's great that everyone could come and get together and talk about Bazel. And I really believe we will make it better together with a lot of feedback and thinking through what are the best ways to address it. So thanks so much. I hope you have a great day, and I wish I was there.
So you've heard a little bit from Melody about how Google tries to push more tests and push its testing earlier in the development cycle so that we catch bugs sooner and we improve developer productivity and we can move faster. So I want to show you just a little example of how having the right tooling that can help you push those things earlier can really help increase developer productivity and help improve your software. If we can switch over to the demo machine. There it is. So I'm connected to a machine here that is set up to build TensorFlow. And I'm going to use Bazel to build part of TensorFlow. So Bazel starts up, it builds this dependency graph, and it starts compiling things. And things are running along nicely. You can see this is a 16-core machine. It's about 60 gigs of RAM, reasonably powerful machine. And you can see it's running 16 things in parallel, which is great. And Bazel does a great job of creating that graph and figuring out what we don't need to execute. The only problem is you can see we're at about 150, 200 actions right now. This is part of the TensorFlow project. This part takes about 8,500 actions to complete. So this build is probably going to take about 15 minutes or so to finish. And if I were a developer, I would be thinking, OK, I guess I'll go read some email, get a cup of coffee, something like that. But I literally just got started. This is the first thing I did was build my tree and try to test to make sure that everything's working in a clean state. So we would really love to speed this up. And there is a way to speed this up. So Melody talked about how we can run more things in parallel and we can offload these things to the cloud. So this is a similar machine set up for Bazel to distribute things to the cloud. And I've kicked off the build. You can see all of a sudden, we're not running 16 things in parallel. We're running 500 things in parallel. So this build's going to take a lot less time. It still takes a little time, because it's a completely clean build from scratch. I synced the tree this morning. If we can switch back over to the slides quickly. This is also a 16-core machine, although, to be honest, it doesn't need those 16 cores. The machine is largely sitting idle because it's sending everything up to the cloud. But I wanted to do an A/B comparison, so I kept the machines the same. So why is this possible? So this all goes back to the idea of Bazel creating actions that are fully specified and hermetic and deterministic. So if you know what all your inputs are, and you know what your action is going to look like, and you've done a good job of fully encapsulating that, there's no reason why that action needs to be run on your local machine. So Bazel grabs all that information, sends it up to a cloud service, and then the cloud service executes things and then sends back the results. So things can just be run in much, much greater parallelization, as you saw, 16 to 500. And that's really limited by the amount of parallelization available in your build graph. Anything we can run in parallel, we do. So TensorFlow tops out at about 500. As it turns out. So in terms of understanding what this looks like, obviously there are some very obvious inputs to your build, things like your source files, your data files that exist in your repository, any libraries that you've built in other parts of your repository that you need for your binaries that you're building, your tests that you're running, the command line itself, the parameters you're passing to the program, things like that. And there are some inputs that are a little bit more subtle. Things like the installed software on your machine. What version of JavaC or GCC or Clang are you running? What other utilities is your software invoking? What system libraries are you linking in, et cetera? So Bazel grabs all those things, packages them up in a little proto format, and sends it up to the cloud. And the cloud figures out, OK, I can set up this environment. I can execute this action. I can run this action, and it'll run it, send back the results. They come to your local machine. You can view the test logs the same way. You see the test results the same way, et cetera. So if we can flip back to the demo machine. So just a quick status check. This is our local build. You see still running 16 things in parallel, about 1,300 actions, so we've still got a while to go. If we go to the remote machine, though, we've run 8536 out of 8537. So we have one long test here, that should complete momentarily. But you can see I'm going to be waiting quite a while on this build for this to finish. And maybe this is a good example of why you run your tests first when you develop things, because maybe this test is going to fail. So you know what's happening. So I've already saved myself maybe 10 or 15 minutes of time by doing this. I'm actually just going to cancel out of this build because we're a little short on time. We skipped a test, but I want to show you what happens when you make a change. So now I've figured out I have a clean baseline. I'm going to go into my source code and say, yeah, I want to change this. I've got this, this constant here, string constant, scope to a local function. I think it might actually be useful to pull it out, use it somewhere else. So I'm going to pull it out to the namespace scope and delete it from the local scope. And then I will rerun. So Bazel, once again, creates this graph of actions. And it says, OK, what do I already know about? What don't I need to compile? And the answer is most things I don't need to compile. So it's going to send basically a couple build actions and then those 216 tests back up to the cloud. And we'll rerun those. Takes a few seconds. We can actually, I do want to show one more slide if we can flip back to that. So you can see this is going back to the same imagery we had before. You invoke Bazel. It creates this whole build graph. It checks with your local cache to see what exists locally and screens out, filters out a bunch of actions it doesn't need to run. Then it checks with the cloud cache and says, OK, what does the cloud know about? And this isn't just things on my machine. This is things that any developer or any CI system that's connected to the system has already run. So you can see the cloud cache there is a lot larger than your local cache. It holds a lot more historical data, a lot more data across different revisions and things like that. So you end up with a pretty small list of actions that need to be run. Those get sent up to the cloud. And if we switch back to the local or to the demo machine, you can see, oh, I made a mistake. What did I do? I will go check the log file, which is here. And it tells me, oh, 0, 1. Oh, I know what I did. I can go back to this file. I put the 0 at the end because that's the way they are on the keyboard. But it should look like this. And I can do that and rerun, and it'll do those tests. So you can see that this, I'm still waiting. I'll check on this other build. Oh, 1,800 actions. I'm getting a second cup of coffee. So you can see that just by having the right tools, it means that I can run tests faster, I can run them more often, I can run them earlier in my development cycle, and I can catch things sooner. I'm not waiting for the nightly test run. I'm not waiting for post-submit runs. I'm not even waiting for pre-submit. I'm running them locally on my machine. So it really tightens up that development loop and saves a lot of time. So this is a system. This is running against a system called Cloud Build for Bazel. Bazel has the ability built into it to talk to a number of different remote build systems. Cloud Build for Bazel is part of the GCP Google Cloud platform. You'll hear more about it later today. But we use a very similar system internally with Bazel for Google across those 4 million builds per day to run all of our tests. And because this is Bazel and everything's open source, there are actually several open source implementations that you can build and self-host yourself as well. And they all have different optimizations, different trade-offs. But I hope you come back this afternoon and hear a little bit more about remote builds and remote caching.